Hello there, and welcome to the Sleepy Science Channel. Tonight, we are traveling to the edge of the known universe. Not a boundary you can touch, and not a wall waiting in the dark, but the farthest limits that science has reached. This is a journey into mysteries at the very edge of our cosmos. The universe may continue far beyond anything we can see, but those regions might always remain hidden. Even the word edge begins to change meaning when space itself is expanding. As we look farther away, we also look deeper into the past. The most distant signals do not show us the universe as it is now. They show us its earliest visible state, when everything we know was still taking shape. Some ideas tonight are firmly grounded in evidence. Others belong to the frontier where physics becomes speculation, and this is where the subject becomes truly fascinating. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is get settled in. Let your shoulders soften, let your breathing slow, and allow your mind to settle into stillness as we explore the edge of the universe together. Let's begin. The universe may have no edge we could ever reach. It is natural to imagine an edge as a distant boundary, like the shore of an ocean or the rim of a map. But the universe may not work that way at all. In modern cosmology, space is not treated as a container with walls. It is the thing being measured. If it is infinite, then no journey, however long, could arrive at a final border. If it is finite, it could still curve back through itself, so that traveling in a straight line would not lead to an outside. It would be more like moving around the surface of Earth, where no cliff marks the end of the world. This idea is difficult because it asks the mind to give up the picture of space as a room. There may be no final fence. There may be no last star. The universe may simply continue, either without limit or in a shape too large for us to detect. The observable universe ends where ancient light finally runs out. When astronomers speak about the edge we can observe, they are not describing a physical border. They are describing the limit of light that has had enough time to reach us. The universe has existed for a vast but finite age, and light, though incredibly fast, does not travel instantly. That means there are places so distant that their signals are still on the way. They may be real, filled with matter and history, yet invisible to every telescope we can build today. The farthest light we do receive is not showing nearby objects as they are now. It is showing ancient conditions from a much younger cosmos. This makes the observable boundary more like a time limit than a wall. Our view is shaped by cosmic patience. Each year, a little more light has had time to arrive, but the deeper truth remains humbling. We see only the part of reality that has had time to speak. Beyond our cosmic horizon, there may be endless unseen galaxies. The cosmic horizon is one of the most powerful ideas in astronomy, because it separates what can be known from what may exist. Beyond it, there could be regions much like ours, with galaxies gathered in clusters, stars burning through their lifetimes, and planets circling suns no eye will ever see. There is no evidence that space simply stops beyond the limit of our sight. In fact, the part we can study appears smooth and consistent on enormous scales, which suggests the unseen cosmos may continue with the same broad pattern. Yet those places are not merely far away. They are hidden by the structure of space-time and the history of expansion. Their light has not reached us, and in some cases it may never do so. This gives the universe a strange kind of double nature. It is measurable in one direction and unknowable in another. The darkness beyond our view may be filled with whole cosmic histories. The edge we can see is not the edge of everything. The deepest mistake is to treat the limit of our vision as the limit of existence. Humanity has made that mistake before. The horizon at sea once looked like a boundary, yet ships returned from beyond it. The Milky Way once seemed like the whole universe, until other galaxies were revealed. Today, our telescopes reach astonishing distances, but the same lesson still applies. Seeing farther does not mean seeing all. The cosmic boundary around us is created by time, light, and expansion. It tells us where our evidence fades, not where reality must end. This distinction matters because it keeps science honest. We can describe the observable universe with confidence, while still admitting that the total universe could be far larger. It may even be infinite. The visible cosmos is not small, but it may be only a local patch of something beyond complete measurement. The edge of sight is a magnificent limit, but not a final answer. Space itself expands faster than distant light can cross it. Nothing can move through space faster than light, but space itself is allowed to stretch in a way that makes faraway regions separate faster than light could bridge them. This sounds impossible at first, because everyday experience tells us motion must belong to objects. Cosmic expansion is different. Galaxies are not always racing through space like sparks from an explosion. Instead, the distance between them grows as the fabric of space changes scale. Across small distances, gravity can hold things together. Across unimaginable distances, expansion becomes the dominant effect. A photon may travel faithfully toward us for billions of years, while the space it crosses keeps lengthening beneath its path. In the most extreme cases, the destination slips away faster than the light can make progress. This is why the universe can contain places that are not merely difficult to reach, but unreachable in principle. Space is not passive scenery. It is an active part of the story. Some galaxies are already vanishing beyond our future forever. There are galaxies whose ancient light is still arriving now, so we can photograph them and study their histories. Yet because the universe has expanded during the long journey of that light, those same galaxies may already be beyond any possible future contact. We are seeing old news from places that have slipped past a cosmic point of no return. If they emitted a new signal today, that signal might never reach the Milky Way, no matter how long we waited. This is one of the most startling consequences of accelerated expansion. The universe does not only reveal itself, it also hides itself, gradually and permanently. Future astronomers may look out and see a much emptier cosmos, because the evidence of distant realms will have faded beyond reach. Our era may be unusually rich in cosmic information. We live at a time when the universe is still generous with its past, even as parts of its present become unreachable. The universe may be infinite, with no outside at all. Infinity is not just a large number with more zeros than we can imagine. It is a different kind of idea. If the universe is infinite, then asking what lies beyond it would be like asking what number comes after all numbers. There would be no outside region because space would not occupy a larger room. It would be the full arena in which location has meaning. This possibility is supported by measurements showing that space appears extremely flat on the largest scales we can observe. Flatness does not prove infinity, but it fits comfortably with it. The unsettling part is what infinity implies. Any pattern allowed by physics might occur somewhere, not once but again and again, separated by distances beyond comprehension. Yet none of this can be reached or confirmed directly. An infinite universe would turn the edge into a human expectation rather than a cosmic feature. The mind wants a boundary. Reality may not provide one. The farthest light shows the universe as a newborn glow. The most ancient light we can detect did not come from stars. It came from a time before stars had begun to shine. Early space was filled with hot material that scattered light constantly, like a dense glowing haze. As the universe expanded and cooled, electrons joined with nuclei to form neutral atoms. Suddenly, light could travel freely instead of being trapped in repeated collisions. That released glow still fills the universe today, though expansion has stretched it into microwaves far too cold for human eyes. It is not a picture of one distant object. It is a picture of the young cosmos everywhere at once. When scientists map it, they see tiny temperature differences that later grew into galaxies and clusters. This glow is a fossil made of light. It carries evidence from a time when the universe was simpler, hotter, and far more uniform than the star-filled place we know now. The edge of sight is really an edge in time. Looking into space is unlike looking across a landscape. When you see a nearby hill, you see it almost as it is now. When you see a distant galaxy, you see it as it was when its light began the journey. The farther we look, the older the message becomes. This turns the telescope into a kind of time instrument. A galaxy at great distance may appear young, not because it still is, but because we are receiving light from its youth. This means the visible boundary of the universe is not arranged like a fence around us. It is layered by history. Nearby space shows recent events. Distant space shows earlier chapters. At the deepest reach, we do not see modern galaxies at all, but traces from a universe before ordinary structure had formed. The edge of sight is the place where distance and history become the same thing. It is not just far away, it is long ago. We may live inside only one bubble of a greater cosmos. Some versions of inflation suggest that our universe could be one settled region inside a much larger cosmic process. In this picture, space expands at an extraordinary rate in some places, while pockets stop inflating and form bubble universes. Each bubble could develop its own conditions, perhaps with different values for the forces and particles that shape nature. Our entire observable universe would then be inside one of these regions, enormous from within, yet only one part of a wider reality. This idea is speculative, but it grows out of serious attempts to understand the earliest moments of cosmic expansion. The challenge is evidence. Other bubbles, if they exist, may be forever beyond contact. Some scientists have searched for possible marks left by collisions between bubbles, but no convincing signal has emerged. Still, the possibility is breathtaking. What we call the universe may be local. The greater cosmos, if real, could be a landscape of many beginnings. The observable universe is shaped by the speed of light. Light is the universe's messenger, but it has a speed limit. That single fact shapes everything we can ever observe. If light traveled instantly, the entire cosmos might be visible at once. Instead, every signal takes time, and the age of the universe sets a boundary around our knowledge. The farther something is, the longer its light has been traveling. At some distance, there has simply not been enough time for any message to arrive since the beginning of cosmic history. This does not mean nothing exists there. It means information from there has not reached our location. In a strange way, the speed of light gives the universe a visible size. It creates a sphere of possible evidence around every observer. This sphere is not painted onto space. It is created by time itself. Our cosmic view is therefore not only about telescopes and technology. It is governed by one of nature's most fundamental limits. Every telescope looks outward and backward at the same time. A telescope does more than magnify the sky. It collects old messages. Even the moon is seen with a slight delay, because its light takes a little time to reach Earth. Sunlight is older still by the time it warms your face. Across interstellar and intergalactic distances, that delay becomes enormous. A telescope aimed at a remote galaxy may gather photons that left before Earth had complex life, before the Sun had finished many of its journeys around the Milky Way, or before our galaxy had its current shape. This gives astronomy a remarkable power. It can study change across cosmic history without needing a time machine. Different distances reveal different eras. Nearby galaxies show recent evolution, while faint remote galaxies reveal early stages of assembly. The sky is not a single present moment. It is a layered archive. Every deep image is a mixture of distance, age, and memory, captured in light that has survived the journey. The cosmic horizon grows as older light finally reaches us. The boundary of what we can observe is not completely frozen. As time passes, light from slightly more distant regions has time to arrive. In that sense, our observable universe grows. But this growth is not simple. Expansion changes the distances while the light travels, and dark energy affects which signals can ever reach us. Some ancient photons that were once beyond our view will eventually arrive, adding new information to the cosmic record. At the same time, there are present-day events so far away that their signals will never catch up to us. This creates a strange balance. The past can continue revealing itself, while parts of the present disappear forever beyond contact. The horizon is not a wall that sits still. It is a moving limit shaped by cosmic age and cosmic expansion. Over billions of years, the universe offers more of its ancient history, even as its living distance grows more unreachable. Some regions exist but can never send us their light. There may be places in the universe that are real in the same physical sense as our own region, yet forever outside communication. Their galaxies could shine, their stars could die, and their planets could turn. But no beam of light from their present could ever reach us. The reason is not that the light is weak. It is that expansion carries the space between us apart too quickly over enough distance. A signal can travel at the maximum possible speed and still lose the race against the growing gap. This creates a boundary deeper than ordinary remoteness. It is a separation in cause and effect. We cannot influence those regions, and they cannot influence us now. For science, this is a hard limit. For the imagination, it is staggering. Reality may contain chapters that are physically connected to the same grand cosmos, yet permanently absent from our evidence. They exist beyond the reach of conversation. Expansion can separate galaxies without pushing them through space. The easiest picture of the universe is an explosion, with galaxies flying outward from a central blast. That picture is misleading. Cosmic expansion is not mainly galaxies moving through a pre-existing emptiness. It is the growth of distance built into space itself. A useful way to think about it is to imagine points on a stretching surface. The points are not driving across that surface, yet the separations between them increase. In the real universe, gravity complicates the story. Galaxies inside clusters can remain bound together, and the Milky Way is not being stretched apart from its nearby companions. But across the largest scales, expansion dominates. This is why distant galaxies appear to recede from us, and why the farther ones recede faster. They are not fleeing from our location in any special way. Every observer in the expanding universe would see a similar pattern. Space is growing, and the galaxies reveal that growth by their increasing separation. The universe has no known center and no known border. When people hear that the universe is expanding, they often imagine everything rushing away from a middle point, but observations do not show a preferred center. On large scales, the universe looks broadly similar in every direction, once local structure is averaged out. That means expansion is not pointing back to one special location in space. Instead, every distant observer would see other faraway galaxies receding in a way much like we do. This is one reason the balloon surface analogy is so useful. A two-dimensional creature living on the surface would see distances grow without finding a central point on the surface itself. The center, in that analogy, is not part of the creature's universe. Our reality is more complex, but the lesson is powerful. The cosmos does not appear arranged around us, or around any other known place. It has no observed middle and no observed outer rim. That absence is part of its grandeur. The Big Bang happened everywhere, not at one central point. The name can make it sound like an explosion that began at a spot and expanded into surrounding emptiness. Modern cosmology describes something far stranger. The early universe was not a small object sitting inside space. It was space itself in a hot, dense state. As it expanded, distances grew everywhere. This means every region we observe was once much closer to every other region, not because they were all gathered around a central spark, but because the scale of space was smaller. No matter where you are in the universe, if you look far enough back in time, you trace your region toward that same dense beginning. This is why there is no special direction to point and say, there is where it happened. It happened here too. It happened in the matter that became the Milky Way, in the matter that became distant clusters, and in all the regions whose light we may never receive. The origin was everywhere. The farthest visible thing is not a star or galaxy. The deepest view in the universe is not a single shining object. It is a background glow that comes from all directions. This ancient radiation was released before stars, planets, and galaxies existed, when matter had cooled enough for light to travel freely. Because it surrounds us, it does not behave like a point in the sky. Wherever a sensitive microwave telescope looks, it finds the same ancient signal, with tiny variations that carry immense meaning. Those variations are the early fingerprints of structure. Slightly denser regions later drew in more matter through gravity, becoming the seeds of the cosmic web. This makes the oldest visible signal both simple and profound. It is almost uniform, yet not perfectly smooth. That small unevenness is why the later universe could become interesting. The farthest thing we can study is therefore not a distant island of stars. It is the early universe itself, spread across the entire sky as a relic of light. Ancient microwave light surrounds Earth from every direction equally. No matter which way a radio telescope turns, it detects a faint afterglow from the young universe. This radiation is extraordinarily even, which is one of the great clues that the early cosmos was once in a hot, dense, highly uniform condition. Its temperature is now only a few degrees above absolute zero, because expansion has stretched and cooled the original light for billions of years. Yet hidden inside that smoothness are tiny differences, measured with astonishing precision. Some patches are slightly warmer, others are slightly cooler. These small variations are not random decoration. They reveal the early pattern of matter and energy that later grew into the large-scale structure of the cosmos. To receive this light is to be surrounded by evidence from a time before familiar objects existed. It reaches us from every direction because it was released everywhere. The whole sky becomes an ancient surface, carrying the memory of a universe just becoming transparent. The cosmic microwave background is a wall of earliest visibility. This ancient glow is sometimes described as a surface, but it is not a solid shell around the universe. It is the limit beyond which ordinary light could not travel freely. Before that stage, photons were trapped in a thick plasma, constantly scattered by charged particles. The universe was bright, but impossible to see through. When neutral atoms formed, the fog lifted, and light began its long journey across space. That release created the earliest direct image available to astronomy. It is like looking at the moment the cosmic curtain opened. Anything earlier must be studied indirectly, through mathematics, particle physics, and subtle imprints left behind in later signals. This makes the background glow one of the most valuable sources of evidence in all science. It marks the boundary between visible history and hidden origin. Beyond it lies not empty space, but an earlier condition where the usual idea of seeing simply breaks down. Our first clear view begins there. Before that first light, the universe was glowing fog. In the earliest visible chapter of cosmic history, space was filled with a dense mixture of particles and radiation. Light existed, but it could not travel freely. Every photon kept running into charged particles, which scattered it again and again. Imagine trying to shine a torch through a storm of brilliant mist, where the mist itself is made of fire. That is not a perfect picture, but it helps explain why the young universe had no clear view through itself. It was bright everywhere, yet transparent nowhere. This hidden period matters because it contains the conditions that shaped everything that followed. Matter was present, but it had not yet gathered into stars. Gravity had begun its slow work, but the familiar structures of space were still waiting. The universe was not empty before the first clear light reached us. It was active, hot, crowded, and full of potential. The story was already happening, even though no ordinary telescope can look directly into it. We cannot see the universe before it became transparent. There is a real limit to vision built into cosmic history. It is not caused by poor instruments, distance, or human weakness. It exists because earlier light was trapped inside a dense sea of charged particles. Before neutral atoms formed, photons could not travel in straight paths across great distances. They were constantly scattered, so no clear image from that time could survive. This is why telescopes, even the most advanced ones, cannot simply peer past the first visible glow and take a picture of the universe at an earlier stage. To study that hidden age, scientists must use indirect clues. They look at particle physics, gravity, the patterns in ancient radiation, and the later arrangement of galaxies. It is detective work on the largest possible scale. The invisible past has not vanished completely. It left fingerprints, but it did not leave a photograph. The first direct view begins only after the universe cleared enough for light to travel freely. The edge of sight is wrapped around us completely. The farthest visible boundary is not located in one direction. It surrounds every observer like a sphere of ancient information. Look north, south, or toward any point in the sky, and the deepest reachable signal comes from the early universe. That can feel strange because we are used to edges being places you approach from one side. This boundary is different. It is a limit created by the time light has had to travel toward us from all directions. Earth sits at the center of our observable universe, but not because Earth is physically central. Any observer anywhere would find themselves at the center of their own view. This is one of the most humbling ideas in cosmology. The universe does not crown our location with special importance. It simply gives every observer a surrounding horizon. We are enclosed by the oldest light we can receive, and that glowing limit forms a complete sky around us. Every observer has their own private observable universe. A civilization in a galaxy billions of light years away would not share exactly the same cosmic view that we do. Its surrounding horizon would be centered on its own location. Some regions visible to us would fall outside its reach, while some regions visible to it would be hidden from Earth. This means the observable universe is not a single object with one universal boundary. It is a local bubble of information, shaped by where and when the observer exists. That idea changes the way we think about cosmic knowledge. There is no master balcony from which the whole universe can be seen at once. Every viewpoint has limits. Every sky carries a different selection of ancient messages. If distant astronomers exist, they may study a universe that overlaps with ours but is not identical to ours. Science, even at its grandest scale, is always gathered from somewhere. Our cosmic map is magnificent, but it is not the only possible map. An alien galaxy would see a different cosmic horizon. If intelligent observers lived far from the Milky Way, their deepest telescopes would collect a different arrangement of ancient light. They might see galaxies that will never be visible from Earth. They might miss whole regions that we can study in detail. The laws of physics would not change, but the available evidence would. Their history of discovery could follow a different path, because their sky would contain a different archive. Perhaps a major cluster sits near the center of their observable region. Perhaps our galaxy appears to them as a faint, young object from a remote past. Perhaps the Milky Way is beyond their horizon entirely. This does not make one view more true than another. It shows how deeply observation depends on location inside an expanding universe. The cosmos is not laid open equally to everyone. It reveals itself in overlapping portions. Somewhere far away, another astronomer could be asking the same questions, from a horizon we can never see. The universe beyond our horizon may look much like ours. The part we can study appears broadly uniform when viewed on enormous scales. Galaxies gather into clusters. Clusters connect through vast structures, and matter follows patterns that seem consistent across the observable cosmos. Because of this, many scientists think the regions beyond our view may follow the same general rules. That does not mean every distant place would be identical. Local details would vary. Stars would form in different arrangements, galaxies would merge in different histories, and planets would follow their own stories. But the large-scale recipe may remain familiar. This possibility is powerful because it turns the unseen universe into something less like fantasy and more like an extension of measured reality. We cannot prove what lies beyond the horizon by looking there directly, yet the smoothness and consistency of what we do see suggest that the hidden regions may not be wildly different. The unknown may be immense, but it may still belong to the same cosmic pattern. Inflation may have stretched space beyond imagination in an instant. Very early in cosmic history, space may have undergone a burst of expansion so rapid that ordinary intuition fails. In a tiny fraction of time, a microscopic region could have grown into something astronomically larger. This idea was developed to explain several puzzles. The universe looks remarkably uniform in directions that should not have had enough time to exchange heat or information. It also appears very flat on large scales, as if any original curvature was stretched almost smooth. Inflation offers a possible answer. It takes a small, connected region and expands it until once neighboring parts are flung far beyond one another. The result is a universe that looks even, broad, and nearly flat from inside. The remarkable part is that this ancient event may have magnified quantum uncertainty into cosmic importance. Something unimaginably small may have set the stage for everything vast. Inflation remains one of the boldest bridges between the tiniest physics and the largest structures. Tiny quantum ripples may have become the largest cosmic structures. In the early universe, even empty space was not perfectly still. Quantum physics allows tiny fluctuations to appear at microscopic scales. During inflation, those subtle differences may have been stretched across enormous distances. What began as almost imperceptible variations became slight differences in density. Over time, gravity amplified them. Regions with a little more matter pulled in still more matter, while thinner regions became emptier. Billions of years later, those small seeds had grown into galaxies, clusters, and the vast web-like pattern seen across the universe. This is one of the most astonishing ideas in modern cosmology. The largest structures in existence may trace their origin to tiny quantum irregularities from the earliest moments. The universe did not begin as a perfectly smooth stage where galaxies appeared at random. It carried faint instructions from the start. Every great cluster may be the matured echo of a fluctuation once far smaller than an atom. The universe might be far larger than all we observe. The observable universe is already enormous beyond ordinary comprehension, yet it may still be a small portion of the whole. The reason is simple, but profound. We can only observe regions whose signals have had time to reach us. If space extends far beyond that limit, then our telescopes are sampling a local patch rather than surveying the full reality. Inflation makes this possibility even more dramatic, because it may have stretched the total universe to a size so vast that the visible part is almost negligible. We do not know the full scale. It could be finite but immense, or it could go on without end. What we can say is that our measurements do not show a nearby boundary. The cosmos does not seem to be running out just beyond the edge of our view. The part we see may be like a lantern circle in a field at night. Everything inside is real, but it does not prove the field stops there. Some models suggest space continues forever in every direction. A universe with infinite extent is not easy to picture because every object we know has a size. Rooms end. Countries end. Planets have surfaces. But space may belong to a different category. If it is infinite, then there is no farthest galaxy in an absolute sense. There is only the farthest galaxy whose light can reach us. Beyond that, more regions would continue without a final boundary. This idea follows naturally from certain cosmological models, especially those where space is flat on the largest scales. Measurements so far are consistent with near flatness, though they cannot prove infinity. The difference between very large and truly endless may be impossible to settle from inside the observable universe. Still, the possibility is astonishing. Every direction could lead onward forever, not toward an outside, not toward a cosmic wall, just onward through more space, more matter, more history, and perhaps more forms of complexity than we can ever know. A finite universe could still have no physical edge. It may seem obvious that if something is finite, it must have a border. But geometry allows stranger possibilities. The surface of Earth has a limited area, yet a traveler moving across it never reaches an edge. They can keep going and eventually return to where they started. Some cosmological models imagine a similar idea in three-dimensional space. The universe could have a total size without possessing a boundary where space stops. This would mean the cosmos is finite, but unbounded. A journey in a straight line might eventually loop through the whole structure, although only if the universe was small enough and stable enough for that path to matter. Current evidence suggests that if space wraps around, the scale is larger than the region we can observe. Still, the idea is important because it separates size from edge. The universe does not have to be infinite to avoid a war. It may be complete in a way our everyday geometry never prepared us for. Curved space might loop without ever reaching a boundary. Einstein's theory showed that space is not merely an empty stage. It can have shape, and that shape depends on energy and matter. On cosmic scales, this raises an extraordinary question. Could space be curved so that a straight path eventually returns to its starting point? In such a universe, direction would be deceptive. You would not hit a barrier or fall over an edge. You would continue forward through ordinary space, while the larger geometry quietly guided the path back around. This is difficult to visualize because human minds evolved for small, nearly flat environments. We handle tables, roads, rooms, and hills. We do not naturally picture three-dimensional space bending through itself. Astronomers test these ideas by studying ancient light and searching for repeated patterns in the sky. So far, no clear loop has been found. Yet the possibility remains one of the most elegant ways the universe could be finite without ever ending. Traveling straight forever might someday bring you back home. In a wrapped universe, the most adventurous journey would not lead outward to a rim. It would lead around the total shape of space. A traveler with impossible patience and technology might move in one direction for ages, past galaxies that become unfamiliar, cross regions beyond our current horizon, and eventually return from the opposite side. This is not a claim that such a voyage is possible in practice. Cosmic expansion, lifespan, energy, and the speed of light make it far beyond realistic travel. But as a geometric idea, it is astonishing. It turns the universe from an endless desert into a shape with hidden continuity. The path never breaks, yet it may close. The traveler never turns, yet home appears ahead. This possibility has inspired serious searches for signs that the sky repeats itself. If light has wrapped around the universe, we might see the same ancient region in more than one direction. So far, the sky keeps its secret. No spacecraft could outrun the expansion of distant space. Human engineering can build astonishing machines, but cosmic expansion sets a limit beyond any engine. A spacecraft moving through space can never exceed the speed of light. Over ordinary distances, that is not the issue. The Moon, Mars, and even nearby stars are difficult but conceptually reachable. The problem appears at extreme cosmic scales. Some regions are being carried away by expanding space so quickly that no signal or ship sent now could ever reach them. Adding more fuel would not solve it. The gap itself grows too fast over the whole distance. This makes the universe more like a landscape with moving possibilities than a static arena. There are destinations that are visible in old light, but unreachable in future travel. Even a civilization with technology far beyond ours would still face horizons written into space-time. The edge of exploration is not only a matter of courage or invention. It is also a matter of geometry and cosmic time. The most distant galaxies appear young because their light is ancient. When powerful telescopes capture extremely remote galaxies, they are not seeing those galaxies in their present condition. They are seeing light that left when the universe was much younger. This is why distant galaxies often look small, clumpy, bright with star formation, or unfinished compared with mature galaxies nearby. Their appearance is a preserved stage in their development. It is like receiving a photograph of the city taken during its construction, long after that city may have changed beyond recognition. The farther the galaxy, the older the image. This makes deep space observations a record of cosmic growth. Nearby galaxies help us study what long evolution can produce. Remote galaxies show earlier experiments in structure when matter was still assembling into stable forms. The strange thing is that these ancient images arrive now, inside our own modern sky. We look outward and meet the past face to face. Distance turns into biography, and every faint galaxy becomes a chapter from youth. Webb sees galaxies near the dawn of cosmic structure. The James Webb Space Telescope was designed to collect infrared light, which is crucial for studying the early universe. As space expands, light from very distant galaxies stretches toward longer wavelengths. What began as ultraviolet or visible light can arrive as infrared after crossing billions of years of expanding space. Webb can detect that stretched light with extraordinary sensitivity. This allows scientists to study galaxies from a time when cosmic structure was still young. Some appear surprisingly bright or developed for their age, which has made astronomers reconsider how quickly the first galaxies grew. Webb does not break cosmology by finding these objects, but it sharpens the questions. How efficiently did early gas collapse into stars? How quickly did black holes form? How fast did galaxies assemble mass? Every deep observation adds another clue. The telescope is not simply taking beautiful pictures. It is reading faint evidence from an era when the universe was learning how to build. Early galaxies challenged simple ideas about how fast structure formed. Before the latest observations, many models suggested that the first galaxies would be faint, small, and slow to assemble. Some were expected to grow gradually as gas collected inside dark matter halos. Then, deeper surveys began finding early candidates that appeared brighter, more massive, or more numerous than expected. These discoveries do not mean the whole scientific picture is wrong. They mean the early universe may have been more efficient at building structure than simple assumptions suggested. Gas could have cooled rapidly. Star formation may have happened in intense bursts. Early black holes might have grown faster than expected. Measurements are difficult at these distances, so each claim requires careful checking. Still, the excitement is real. The first galaxies were not just weak sparks appearing timidly in darkness. Some may have emerged with surprising force. The young universe may have been more dynamic than our neat timelines allowed, and that makes the edge of observation feel alive with revision. The first stars may have burned huge and brief. The earliest stars formed from nearly pure hydrogen and helium, because heavier elements had not yet been forged in abundance. Without those heavier elements, gas cooled differently, and the first stars may have grown far more massive than most stars born today. Some may have lived fast, burned intensely, and died after only a few million years. That is brief by cosmic standards. Their deaths would have changed everything. In powerful explosions, they could have scattered the first heavy elements into surrounding space. Carbon, oxygen, silicon, iron, and other ingredients needed for later planets all had to be made inside stars and released. The first generation did not leave ordinary visible survivors that we can easily identify nearby. Their story is mostly reconstructed from theory and from the chemical fingerprints found in ancient stars. Yet their importance is enormous. They transformed the universe from a simple gas-filled realm into a place capable of rocks, atmospheres, chemistry, and eventually life. Those first stars may lie beyond direct observation forever. The first generation of stars may have shone in a period so distant and difficult to observe that no telescope will ever see an individual example clearly. They were born early, lived briefly, and vanished long before galaxies became mature. Their light has been stretched by cosmic expansion, dimmed by distance, and mixed with later sources. Even the most powerful instruments may only detect their collective influence rather than their separate forms. Scientists search for signs in other ways. They look for unusual chemical patterns in extremely old stars, signals from ancient hydrogen, and the possible glow from early stellar populations. The frustration is part of the wonder. Some of the most important objects in cosmic history may remain unseen as individuals. They lit the path toward everything that came later, then disappeared. Their existence is inferred from what the universe became. Like the first spark in a long fire, they may be known mainly by the transformation they caused. The cosmic dark ages hide between first light and first stars. After the universe became transparent, there was a long interval before the first stars filled space with new light. This period is called the Dark Ages. It was not empty, and it was not meaningless. Hydrogen and helium drifted through expanding space, while gravity slowly strengthened tiny differences in density. Invisible dark matter helped shape the scaffolding where gas would later collect. There were no ordinary stars yet, so the universe lacked the familiar sources of visible light. It was a time of waiting, but not of stillness. Structure was being prepared in the dark. Eventually, dense regions collapsed enough to ignite the first stars, and a new phase began. Studying this hidden interval is extremely difficult. because there are few direct signals. One promising approach involves faint radio traces from ancient hydrogen. If scientists can read them clearly, they may uncover the story of how darkness became the first star-filled dawn. Hydrogen once filled the young universe like a silent mist. Before stars transformed the cosmos, neutral hydrogen was the dominant ordinary atom spread through space. It was simple, abundant, and deeply important. This hydrogen carried a faint radio signature that scientists hoped to detect from the early universe. If measured across cosmic time, that signal could reveal how gas cooled, gathered, and eventually gave way to the first luminous objects. The challenge is enormous. The ancient signal has been stretched to long radio wavelengths, and it is buried beneath foreground noise from our galaxy, human technology, and other sources. Yet the reward would be extraordinary. Hydrogen could provide a map of eras that telescopes cannot photograph directly. It would let us study the universe before galaxies became easy to see. This humble atom with one proton and one electron may be the key to unlocking one of the least explored chapters in cosmic history. The simplest element could tell one of the deepest stories. The first starlight slowly carved bubbles through ancient hydrogen. When the earliest stars and galaxies began shining, their energetic radiation changed the gas around them. Neutral hydrogen absorbed ultraviolet light and became ionized, meaning its electrons were stripped away. Around each bright source, a growing region of ionized gas formed. Over time, these regions expanded and merged. The process is known as reionization, and it marks a major transformation in cosmic history. The universe went from mostly neutral gas to the ionized state seen across much of intergalactic space today. This change did not happen all at once. It unfolded unevenly, with bright regions clearing their surroundings, while darker regions remained neutral for longer. The image is powerful because it shows cosmic dawn as an active process. Light did not simply appear. It reshaped the medium it entered. The first galaxies carved openings through the ancient gas, and those openings grew until the universe became broadly transparent to ultraviolet radiation across vast distances. The universe became visible in stages, not all at once. Cosmic visibility has more than one meaning. The first major change came when the hot, early plasma cooled enough for light to travel freely, creating the oldest background glow. But that did not immediately produce stars, galaxies, and the familiar universe. After transparency, the cosmos entered a darker period. Later, the first luminous objects formed and began altering the gas around them. Gradually, more structures appeared, more radiation spread, and more of space became accessible to different kinds of light. This staged unfolding matters because it prevents a simple picture of the universe switching on like a lamp. Different eras revealed different things. Microwave light opened one window. The first stars opened another. Reionization changed the way later radiation moved through space. The visible universe is therefore the product of several transitions. Each one removed a different kind of veil. What we see today is not just the result of light existing. It is the result of light finally being able to travel. Our horizon carries fingerprints from the universe's first vibrations. The young universe behaved in ways that may seem surprising. Matter and radiation formed a hot, dense fluid where pressure and gravity competed. Gravity pulled material inward, while radiation pressure pushed it outward. This created waves that moved through the early cosmos. They were not sound in the everyday sense, because there were no ears and no air. But they were pressure waves, and their imprint survived. When the universe became transparent, those patterns were frozen into the distribution of matter and radiation. Today, scientists can detect their traces in the cosmic microwave background and in the large-scale arrangement of galaxies. These fingerprints are incredibly useful because they act like a standard ruler from the early universe. By measuring their apparent size, researchers can study cosmic geometry and expansion. It is astonishing to think that the largest surveys of galaxies still carry the memory of waves from the universe's infancy. The early cosmos rang, and the pattern remains. The oldest light still contains patterns from vanished sound waves. Before atoms formed, the universe supported pressure waves moving through a hot mixture of particles and radiation. Those waves left subtle temperature differences in the ancient light that later escaped. When scientists map this light, they do not see a blank glow. They see a precise pattern of warmer and cooler patches. The sizes and strengths of those patches reveal the contents and behavior of the young universe. They help measure how much ordinary matter existed, how much dark matter was present, and how geometry shaped the path of light. The waves themselves are long gone. The conditions that allowed them have disappeared, yet their imprint remains readable after billions of years. This is like finding ripples preserved in stone after the water has vanished, except the stone is the entire sky. The pattern is not decorative. It is evidence. It lets cosmologists test ideas about origin, expansion, and composition with remarkable precision. Space may be flatter than any surface humans can measure. When cosmologists say space is flat, they do not mean it is thin, like a sheet. They mean its large-scale geometry follows the rules familiar from ordinary Euclidean space. Parallel lines would remain parallel, and the angles of a giant triangle would add up as expected. Measurements of ancient light suggest that the observable universe is extremely close to flat. If there is curvature, it is so slight that we cannot easily detect it across the region we can see. This is remarkable because a universe could, in principle, be positively curved like a higher dimensional version of a sphere, or negatively curved like a saddle. Near flatness is one of the major clues that inflation may have occurred, because rapid expansion would stretch curvature until it became almost invisible. The idea also affects the possible size of space. A very flat universe may be infinite, or simply so large that our observable patch cannot reveal its overall shape. A flat universe could stretch onward without bending back. If cosmic space is truly flat on the largest scales, one possibility is that it continues forever in every direction. In that case, there would be no wraparound, no return path, and no hidden global curve leading back to the starting point. A straight line would remain straight without closing into a loop. This is not the only interpretation of flatness, but it is one of the simplest. The difficulty is that observations can only test the region from which light has reached us. Space could appear flat locally while having a subtle global structure far beyond our horizon. Still, the measured flatness is striking. It suggests that if the universe is curved, the curve is extraordinarily broad. For anyone imagining an edge, flatness is a challenge. It offers no nearby boundary and no obvious enclosure. It allows the cosmos to be open in a profound sense. The farther you imagine going, the more space may simply continue ahead. Dark energy is making the distant universe disappear faster. Dark energy is the name given to whatever is driving the accelerated expansion of the universe. Its effect is not noticeable inside galaxies, solar systems, or the human body. Gravity and other forces dominate there. But across the vast spaces between distant galaxy clusters, dark energy changes the future. It causes expansion to speed up, which pushes more regions beyond eventual contact. This does not mean galaxies wink out instantly. Their old light can keep arriving for a long time, but their future signals become increasingly unable to reach us. The universe grows more isolated on the largest scales. Dark energy is especially mysterious because scientists can measure its effect more easily than they can explain its nature. It may be related to the energy of empty space itself, or to something deeper in physics. Whatever it is not a small detail. It controls the long-term fate of cosmic visibility. Future astronomers may see fewer galaxies than we do. There may come a time, far in the future, when observers in the Milky Way's descendant galaxy look outward and find a far emptier sky. Distant galaxies that we can still detect today will have receded beyond practical observation. Their light will be stretched, weakened, and delayed until the evidence becomes inaccessible. Local stars and nearby remnants may remain, but the grand cosmic context could be hidden. This means our present era may be privileged in a scientific sense. We can still observe the expansion of the universe, the ancient background radiation, and countless galaxies beyond our local group. Future astronomers might have to infer a larger cosmos from sparse clues, or they might never discover it at all. The thought is both strange and moving. Knowledge itself has a cosmic season. We are living during a time when the universe still displays much of its history. One day, the sky may keep more of that history to itself. One day, other galaxies may vanish from possible discovery. The galaxies do not need to disappear in their own neighborhoods for them to disappear from ours. Their light can be stretched to wavelengths too long and too faint to detect. Their future signals can fall beyond the reach allowed by accelerated expansion. Over immense timescales, the observable universe will become increasingly local. The great population of distant galaxies will fade from view, not because they are destroyed, but because the connection between us and them becomes too thin to carry useful information. This gives cosmic exploration an unexpected urgency. We often think of astronomy as timeless because stars and galaxies live for such long periods. Yet the evidence available to any civilization changes with the age of the universe. There are things we can study now that may not remain discoverable forever. The deep sky is not a permanent library with every book always on the shelf. Some volumes are slowly being carried beyond the door. The night sky may slowly lose its deepest history. The stars in our own galaxy will remain visible for a long time, and nearby galaxies will still shape the local sky. But the most distant chapters of the cosmos are not guaranteed to stay readable forever. As expansion continues, ancient signals from faraway galaxies become stretched to longer and longer wavelengths. Their light grows fainter, colder, and harder to separate from the background. What is a measurable clue today may become a whisper too weak for any future instrument. This matters because the night sky is more than scenery. It is a record of where the universe came from, how it changed, and how structure grew from early simplicity. In the far future, that record may be harder to recover. A civilization born much later might see a universe that appears smaller and lonelier than ours. They might not realize how much has slipped beyond the reach of evidence. The sky would still be beautiful, but its deepest memory could be fading. Cosmic expansion is quietly erasing evidence of the Big Bang. The strongest clues about the universe's beginning are not carved into stone. They are carried by light, motion, and the large-scale arrangement of matter. Those clues depend on being observable. Over vast stretches of time, expansion can make some of them harder to detect. The ancient background glow becomes colder as its wavelengths stretch. Distant galaxies drift farther away, and their light becomes increasingly redshifted. The pattern of cosmic expansion itself may become less obvious to observers trapped inside a future island of gravitationally bound stars. This does not mean the Big Bang stops being true. It means the evidence could become hidden from those who arrive too late. Science depends on the universe leaving traces that can be measured, and those traces are not equally available in every era. We happen to live when many of them are still within reach. In a distant age, the same cosmos may tell a far less complete story. Distant galaxies cross horizons no traveler could ever follow. Imagine a galaxy whose light still reaches our telescopes, giving us a real image of its earlier life. Now, imagine trying to chase it. Even with a perfect spacecraft moving as fast as physics allows for matter, the journey could fail before it begins. The issue is not simply distance. It is the future growth of the space between here and there. At certain scales, expansion creates horizons that separate reachable from unreachable. Once a galaxy is beyond such a horizon, no traveler leaving now could ever arrive, and no message sent now could ever return. This turns the cosmos into a place where visibility and accessibility are not the same thing. We can look at a past version of something that is already outside our future path. That is one of the strangest truths about the universe. Some destinations are real, luminous, and scientifically meaningful, yet they belong to a side of existence that motion can never regain. Their old light can arrive while their present is unreachable. A telescope can receive a signal that began long ago, even if the source has since moved beyond any possible contact. This is one reason deep space feels so strange. The photograph is honest, but it is not current. It shows what the source was when the light departed, not what it is now. During the time that light crossed the universe, the separation between us and the source kept changing. The galaxy in the image may have evolved, merged, faded, or formed countless new stars, yet those newer updates may never reach us. We are allowed to know part of its past, while being denied its present. That situation has no everyday equivalent. On Earth, if we can see a lighthouse, we usually imagine we could travel toward it. Cosmology breaks that instinct. Some beacons shine to us from history, while their living reality has passed beyond the final line of communication. The edge of the universe depends on when you ask. There is no single cosmic boundary, but stays the same for every age. At one time, certain galaxies may be visible. Later, different ancient signals may finally arrive, while other future signals become impossible. The observable universe changes because time passes and space expands. A civilization born earlier would have had a younger, smaller, observable region. A civilization born later may receive more old light from some directions, but lose practical access to distant living galaxies. This makes the edge a moving idea rather than a fixed landmark. It is connected to the age of the cosmos, the behavior of expansion, and the particular moment of observation. Even the phrase, "the universe now," becomes difficult at great distances, because there is no simple way to define a universal present across all of space. The edge is not only a place we cannot reach. It is a changing relationship between light, time, and the observer asking the question. There is a particle horizon and an event horizon. Cosmology uses more than one kind of horizon because the universe has more than one kind of limit. The particle horizon concerns what light has had time to reach us since the beginning. It marks the boundary of what can be observed from the past. The event horizon concerns what can ever affect us in the future. It marks the boundary of possible communication going forward. These two ideas are easy to confuse, but they describe different cosmic questions. One asks, what have we been able to receive so far? The other asks, what could ever reach us if time continues indefinitely? In an accelerating universe, the second boundary becomes especially important. Some things we can see now are already beyond future exchange. They belong inside our particle horizon, but outside our event horizon. That distinction is mind-bending because it separates knowledge from connection. We can possess evidence from places that no longer belong to our reachable future. One horizon marks what we see from the past. The visible universe is built from signals that have already arrived. Every photon captured by a telescope carries a completed journey. The horizon associated with this past light tells us how far back our evidence can extend. It is a boundary of received information, not a surface made of matter. Everything inside it has, in principle, had time to send some signal that could reach our location. Everything beyond it has not yet had that chance. This horizon grows as the universe ages, because older and older light can arrive. But its meaning remains tied to the past. It is like a historical archive whose shelves expand with time. Each new arrival adds to the record of what once was. What makes this so powerful is that our map of the cosmos is not a map of simultaneous places. It is a collection of ancient messages. The past horizon defines the outer edge of that collection. Another marks what we can ever reach or influence. The future horizon is more severe than the visible boundary. It is not about what has already sent light to us. It is about what can ever be reached from now on. If a region lies beyond this limit, then no action taken here can affect it. No radio message, spacecraft, laser pulse, or burst of information can cross the growing distance in time. This makes the event horizon a boundary of consequence. It separates the universe into regions that can still share a future and regions that cannot. In everyday life, distance can usually be overcome with enough patience or speed. In cosmology, that assumption fails. There are places that no amount of waiting will bring into contact. Their future is sealed away from ours by expansion. The idea is both beautiful and unsettling. It means the universe is not one shared arena in the practical sense. It is divided into futures that can never meet. Most of the universe may already be causally separated. To be causally connected means that events can influence one another through signals traveling at or below the speed of light. On smaller scales, this is how the universe behaves. The Sun affects Earth. Galaxies interact with their neighbors. Gravity shapes clusters. But across immense distances, expansion can place regions outside each other's causal reach. If the total universe extends far beyond what we can observe, then the portion able to exchange information with us may be only a limited part of reality. Even within the observable region, some sources seen in old light may have futures that are no longer connected to ours. This changes the emotional shape of the cosmos. It is not simply vast. It is partitioned by possibility. Many places may be real without being able to participate in our story from now onward. The universe may contain countless events that happen in complete independence from us, not because they are unimportant, but because space-time allows no conversation. Causally separated regions can exist without ever exchanging messages. Two regions can belong to the same overall universe and still never communicate. They may follow the same basic physics, grow from related early conditions, and contain the same kinds of matter. Yet if light cannot travel between them, no signal can pass. This idea is central to the limits of knowledge. Science is powerful because it tests reality through evidence. But evidence must arrive. A region beyond causal contact can never confirm itself directly to us, no matter how real it may be. It could contain galaxies, black holes, planets, and observers asking their own questions. From their perspective, we may be the unreachable beyond. Neither side would be hidden by a wall. The separation would be made by the rules of space-time. That is what makes the idea so profound. The universe may be unified in origin or structure, while still divided into domains that never share news. Existence can be larger than communication. The universe may contain places forever outside our story. Human beings naturally turn the cosmos into a story centered on discovery. We build instruments, gather signals, and push knowledge outward. But some parts of reality may never enter that story at all. Not because they are dull, empty, or imaginary, but because no path of information connects them to us. If the universe is vast enough, There may be regions whose entire histories unfold beyond our horizon. Stars could form there. Civilizations could rise there. Black holes could merge there. None of it would leave a mark we could measure. This possibility is not an invitation to fantasy. It is a reminder of how strict the universe can be about evidence. There may be real chapters that never become observable chapters. That thought gives cosmology a rare humility. The map we build may be accurate within its limits, yet those limits may not outline all that exists. Some places may remain outside our story forever. A true edge would raise deeper questions about what surrounds it. If the universe had a literal edge, the next question would arrive instantly. What is beyond that edge? If there is something beyond, then the edge was not the edge of everything. If there is nothing beyond, we must explain what it means for space itself to stop. Ordinary borders make sense because they separate one region from another. A shoreline separates land from sea. A wall separates one room from the next. A cosmic edge would be stranger because space is not simply material within a container. It is the framework in which distance and direction exist. A boundary to that framework would require physics we do not currently possess. This is one reason cosmologists prefer descriptions involving horizons, curvature, or infinite extent, rather than a simple outer wall. The idea of an edge sounds clear at first, but it quickly becomes more mysterious than the universe having no edge at all. Modern cosmology finds no evidence for a cosmic wall. If there were a nearby boundary to the cosmos, astronomers might expect to see some sign of it. Light might behave strangely. The distribution of matter might show a direction of ending. The ancient background radiation might carry a pattern that points toward a border. Instead, the universe appears broadly similar in all directions on the largest scales we can measure. There are local structures, of course. Galaxies form clusters, filaments, and vast empty regions. But no observation has revealed a final wall, rim, shell, or outer surface. That absence does not prove the total universe is infinite. It does mean the simple picture of space ending just beyond our view has no support. The cosmos may have a subtle global shape far larger than the observable region, or it may continue without limit. Either way, the evidence points away from a dramatic boundary nearby. The edge people imagine is not what the data shows. The universe does not seem to expand into empty space. One of the hardest ideas in cosmology is that expansion does not need a surrounding emptiness. When a loaf of bread rises, it expands into the air around it. When an explosion happens, debris moves into pre-existing space. The universe is different. Space itself is the thing whose distances are changing. There is no known external room into which it grows. This is difficult because our minds are trained by objects inside space. Everything we handle has an outside. A balloon has surrounding air. A box has a room around it. But the universe is not just another object in a larger room, at least not in standard cosmology. Expansion means that the metric of space changes, so faraway galaxies become more separated. The growth is internal to the geometry. Asking what it expands into may be applying everyday language beyond its proper range. The universe does not need an outside to increase the distances within itself. Space can grow without needing an outside place. A surface can change its own internal distances without the creatures living on it needing access to a larger dimension. The balloon analogy is imperfect, but it helps with one key idea. Dots drawn on the surface move farther apart as the surface stretches. A creature living only on that surface would measure increasing distances without necessarily knowing anything about the surrounding room. In our universe, the situation is more complex because space has 3 dimensions, not 2. Still, the lesson matters. Growth can belong to geometry itself. It does not have to be motion into a background container. This is why cosmologists can describe expansion mathematically without specifying an outside. The distances between large-scale regions increase according to the evolution of spacetime. The process is not like smoke spreading into a chamber. It is more fundamental. The chamber itself is Changeu. Once this idea settles in, the usual question of what lies outside becomes less obvious and far less necessary. Asking what lies outside space may break ordinary language. Language grew from human experience. It is built for bodies, paths, rooms, skies, and distances we can cross. The word outside assumes a boundary that separates one place from another. But if space itself is the full setting in which places exist, then outside space may not refer to a location at all. It may be like asking what is north of the North Pole. The grammar seems valid, yet the concept has slipped beyond its meaning. This does not mean the question is foolish. It means it may require a different framework before it can be answered. Some speculative theories do imagine larger structures, higher dimensional settings, or other domains beyond our observable cosmos. But those ideas must carefully define what beyond means. Without such a definition, the phrase can mislead us. Cosmology often teaches this lesson. The universe is not only hard to measure, it also forces ordinary words to reveal their limits. The edge of everything may be a limit of thought. The human mind is skilled at finding boundaries. We understand containers, horizons, doors, and endings. So when we think about the universe, we almost automatically picture a final border. Yet the cosmos may not be arranged in a way that satisfies that instinct. The edge may not be a place. It may be a conceptual limit where intuition stops being reliable. Physics has done this before. Time is not absolute. Matter is not solid in the way it feels. Empty space is not simply nothing. Each discovery forced the mind to adjust. The edge of the universe may require the same adjustment. Instead of asking where the wall stands, we may need to ask what can be observed, what can be reached, what can be inferred, and what the geometry allows. The deepest boundary may lie between everyday imagination and mathematical reality. Wonder begins when thought reaches that limit and realizes the universe is under no obligation to be intuitive. Some theories imagine many universes beyond our own horizon. The idea of multiple universes is not one single theory. It appears in different forms across inflationary cosmology, quantum interpretations, and speculative physics. In one version, our observable universe is part of a larger inflating reality that produces many regions with their own histories. In another, quantum events may correspond to branching outcomes, though this is a very different concept from distant cosmic bubbles. What these ideas share is the possibility that what we call the universe might not exhaust reality. This is thrilling, but it demands caution. A proposal is not the same as a discovery. Scientists take such ideas seriously only when they arise from mathematical models that also explain known evidence, or when they suggest possible tests. The challenge is that other universes, if completely disconnected, may be impossible to observe. Still, these theories widen the imagination. They suggest that our cosmic horizon could be not an edge of existence, but a local boundary inside something greater. A multiverse could contain bubbles with different physical laws. If bubble universes exist, they might not all share identical conditions. The strengths of forces, the masses of particles, or the behavior of vacuum energy could vary from one region to another. Even tiny differences might change everything. Stars might not form. Atoms might be unstable. Chemistry might be too simple, or gravity might overwhelm structure too quickly. A universe capable of long-lived stars and complex matter may require a narrow range of conditions. This has made the multiverse interesting to scientists who study why our universe has the properties it does. Perhaps our region is not the only possible outcome, but one among many. We observe this set of laws because this set allows observers to exist. That idea is powerful, but controversial, because it can be difficult to test. It shifts some questions from why must nature be this way to how many ways might nature be. The answer, if real, could be immense. Other cosmic bubbles might be forever impossible to prove. The greatest weakness of many multiverse ideas is not that they are strange. Science has accepted strange things before. The problem is testability. If another bubble universe can never send light, gravity, particles, or any other signal into our observable region, then it cannot be confirmed by direct evidence. It would remain a prediction or consequence of a broader theory, not an observed object. Scientists are careful about this distinction. A model may be elegant, but elegance is not proof. Some researchers have looked for possible traces of past collisions between our bubble and another, perhaps hidden in patterns of ancient radiation. So far, nothing conclusive has appeared. This leaves the idea in a fascinating borderland. It may be a real feature of a deeper cosmic structure, or it may be a mathematical possibility that nature never used. The mystery is not only whether other bubbles exist. It is whether the universe allows us any way to know. Bubble universes could form from inflation that never fully ends. In some inflationary models, expansion stops in certain regions but continues elsewhere. A stopped region can become a bubble universe, with its own hot beginning and later cosmic evolution. Meanwhile, the surrounding inflating space keeps growing, producing more bubbles over time. This process is often called eternal inflation. It is not eternal in every location, but the overall process may continue without a final global ending. The idea changes the Big Bang from a single event into a local beginning within a larger background. Our universe would be one region where inflation ended and ordinary cosmic history began. Other regions could have formed far beyond any possible contact. This picture is speculative, yet it arises from serious attempts to understand how inflation works. Its scale is almost impossible to absorb. Creation would not be a one-time spark, but an ongoing process in a larger cosmic landscape. What we call the beginning may be one beginning among many. Our universe may be one calm region in eternal expansion. If eternal inflation is correct, our observable cosmos could be a settled pocket inside a greater process that still expands elsewhere with extraordinary speed. Inside our region, expansion slowed enough for particles, atoms, stars, galaxies, and planets to form. Outside, in the inflating background, conditions could remain too extreme or too different for ordinary structure. This makes our universe feel less like the whole arena and more like a habitable clearing in a much larger storm of space-time growth. The word calm here does not mean nothing dramatic happens. Supernovae explode, black holes collide, and galaxies merge. It means the basic conditions allow complexity to persist. That alone may be rare in the wider landscape. The idea is speculative, but it gives a new kind of wonder to ordinary existence. Stable physics may not be guaranteed everywhere. The fact that atoms hold together and stars can shine may be a local gift of our particular cosmic region. Parallel universes are possible in some models, not confirmed realities. The phrase parallel universe is often used as though it describes a known place. In science, the situation is more careful. Several models allow realities beyond the one we observe, but none has provided confirmed evidence that such places exist. Some versions arise from quantum mechanics. Others come from cosmic inflation or higher dimensional theories. They are not all the same, and they should not be blended casually. What makes them fascinating is that they emerge from attempts to solve real problems, not merely from imagination. What keeps them uncertain is the lack of direct observation. A responsible view holds both sides at once. The possibility is not nonsense, but it is not established fact. That balance is perfect for a speculative journey. It lets the mind travel far while keeping one hand on the rail of evidence. The edge of the universe, in this sense, is also the edge between what physics permits and what nature has actually done. A larger cosmos may hide beyond every possible measurement. There may be truths about the total universe that no experiment inside our observable region can fully settle. If something lies beyond all possible contact, then it cannot be measured directly, no matter how advanced a civilization becomes. This is a profound limit. We often imagine science as a staircase that eventually reaches every answer. But cosmology suggests some answers may be hidden by the structure of reality itself. We can still build strong models. We can test their predictions inside the observable universe. We can choose theories that explain evidence better than their rivals. Yet the total scale, shape, or variety of the cosmos may remain partly unknowable. This does not weaken science. It clarifies its honesty. Science is not the claim that everything is easily reachable. It is the discipline of saying exactly what the evidence can support. Beyond that, there may be a larger cosmos that remains real, silent, and permanently beyond measurement. The universe may be stranger than any single map. A map gives the comfort of shape. It suggests that if we could step far enough back, we might draw the whole thing clearly. But the universe may not fit into one final picture that satisfies human scale. It may be infinite, finite without boundary, locally observable but globally hidden, or part of a larger process whose full structure cannot be reached. Each map we make is useful within a defined limit. A galaxy map shows the cosmic web. A microwave map shows early radiation. A mathematical model shows possible geometry. None of these alone is the whole. The deepest view may require many maps layered together, each answering a different question. Where is matter? How did light travel? What can influence what? What remains unknowable? The strangeness of the universe is not confusion. It is richness. Reality may be too large, too curved, too old, and too subtle for any single diagram to hold. Cosmic topology asks whether space connects back on itself. Topology studies the way a space is connected, regardless of its exact size or curvature. In cosmology, it asks a thrilling question. Could the universe have a repeated structure, where traveling far enough in one direction eventually brings you to the same region from another side? This would be a kind of cosmic wraparound. It would not require a wall or an outside. It would mean space connects to itself in a particular way. Imagine a video game screen where an object leaving one edge reappears on the opposite side. The real universe, if topologically connected, would be vastly more complex, but the basic idea is similar. Astronomers search for clues in ancient light and galaxy distributions. If space is smaller than it appears in a global sense, patterns might repeat across the sky. No confirmed repetition has been found. Still, topology reminds us that the universe's shape is not only about curvature. It is also about connection. Astronomers search for repeated patterns across the ancient sky. If space wraps around itself, light from the same early region might reach us by more than one path. That could create repeated patterns in the cosmic microwave background, or duplicated arrangements of distant objects. Scientists have looked for such signs with careful statistical methods. They compare temperature patterns across different parts of the sky, searching for matching structures that would suggest the universe is smaller or more connected than it appears. This is extremely difficult because the signals are faint, the sky contains foreground interference, and random patterns can sometimes mimic meaning. The reward would be enormous. A confirmed repetition would reveal something profound about the total shape of space. It would show that the universe is not simply an open spread of galaxies, but a connected geometry with a specific global design. So far, the searches have not produced a clear detection. The sky may not repeat within our observable reach, or the pattern may be too subtle to find. Matching circles in cosmic light could reveal wrapped space. One proposed clue to a connected universe involves circles in the oldest radiation. If light from the same region of the early universe reached us along two different routes, then the cosmic microwave background might contain matching circular patterns. These circles would not be drawn visibly across the sky. They would appear as statistical matches in temperature variations. Detecting them would be like discovering that two distant edges of a map actually describe the same place. It would suggest that space loops back on itself at a scale not much larger than what we can observe. The idea is elegant because it turns ancient light into a test of cosmic architecture. The difficulty is precision. Real data includes noise, foreground signals, and the limited resolution of observations. Searches have placed constraints on certain wrapped shapes, but no accepted matching circles have appeared. Even so, the method is beautiful. It asks the sky whether it has hidden seams. No clear cosmic wrapping has yet been found. So far, the universe has not revealed a confirmed wraparound pattern. Measurements of the ancient background and large-scale structure have not shown repeated regions in a way that convinces the scientific community. This does not prove space is not connected beyond our view. It only tells us that if such a connection exists, its scale may be larger than the observable universe, or its pattern may be too subtle for present methods. In other words, the cosmos may still have a topology we cannot detect. This is a common theme at the edge of cosmology. Absence of evidence can narrow possibilities without closing the mystery. The searches matter because they transform a strange idea into something testable. Scientists are not merely wondering whether space loops. They are asking the oldest light for measurable signs. For now, the answer appears to be no obvious loop within reach. The universe either stretches farther than our tests can catch, or hides its connections very well. The universe may be too vast to reveal its shape. Cosmologists can measure the part of the universe whose light has reached us, but that may not be enough to uncover the whole design. Imagine trying to decide the shape of Earth while standing in a field so flat that the curve is too slight to notice. Your measurements would be accurate, yet incomplete. The universe may place us in a similar position. The region we observe looks extremely close to flat, but the total cosmos could curve on scales far beyond our horizon. It might loop back through a vast geometry, or it might continue without returning at all. If the full shape is larger than the light we can receive, then no telescope can settle the question completely. This is not a failure of science. It is a feature of living inside the thing we are trying to understand. The universe may be so immense that its true form remains hidden, not by darkness, but by scale. Distant light has stretched into redness over billions of years. When light begins its journey from a faraway galaxy, it may leave as blue, white, or ultraviolet radiation. But as it travels, space itself expands, and the light is stretched along with it. Its wavelength grows longer, and longer wavelengths appear redder to our instruments. This effect is called cosmological redshift, and it is one of the great clues that the universe is expanding. It is not the same as ordinary fading. The light is not simply tired, and it is not just losing brightness because of distance. its color has been changed by the growth of space during the journey. The farther the source, the more the light has been stretched before reaching us. In the deepest observations, light that began in one part of the spectrum arrives in another. A galaxy's color becomes a record of cosmic expansion. Every reddened photon carries a message. It says that space changed while the light was on its way. The farther we look, the more stretched light becomes. Distance in astronomy is never just distance. It is also a measure of how much the universe has grown while a signal was traveling. A nearby galaxy has light that has crossed a relatively modest amount of expanding space, so its redshift may be small. A very distant galaxy sends light across a much longer stretch of cosmic history, and that light can be shifted dramatically toward red and infrared wavelengths. This is why the most remote galaxies often require infrared telescopes. Their original visible or ultraviolet light has been pulled beyond the range our eyes could see. Redshift lets astronomers estimate how far back in time they are looking and how much expansion has occurred along the way. It turns color into a cosmic ruler. The deeper we search, the more the universe has marked its own growth into the light. Each distant galaxy arrives altered by the very space it crossed. Redshift tells us space expanded, while photons traveled onward. A photon is a tiny packet of light, and it does not experience time in the way we do. Yet from our perspective, its journey can last billions of years. During that journey, the universe is not frozen. The scale of space changes, and the photon's wavelength grows with it. This is the heart of cosmological redshift. It gives scientists evidence not only that galaxies were far away when their light was emitted, but that the universe expanded during the time the light was traveling. That distinction matters. Redshift is not just a snapshot of motion at the source. It is a history written into the signal. By measuring it, astronomers can reconstruct how the size of the universe changed across different eras. The light becomes a messenger that has been physically transformed by the route it took. In its stretched wavelength, we read the slow enlargement of space itself, preserved in a single arrival. Some light has traveled longer than its current distance suggests. Cosmic distance can behave in ways that feel almost impossible at first. A photon may travel toward us for billions of years, yet the object that emitted it may now be much farther away than the light travel time seems to imply. This happens because space expanded while the photon was moving. The light crossed regions that were smaller when the journey began, but those regions grew along the way. So a galaxy whose light has traveled for over 13 billion years may now be far more than 13 billion light-years away in present-day distance. This is not a contradiction. It is a sign that cosmic distance depends on how you define it. Are you asking how long the light traveled, how far away the source was then, or how far away it is now? Each question has a different answer. The universe teaches us that distance is not always a single number. It is a story. Expansion makes cosmic distances deeply strange and counterintuitive. On Earth, distance feels simple. If a village is 10 miles away, that number does not change much while you walk toward it. In cosmology, the path itself can grow as light crosses it. This creates several kinds of distance, each useful for a different purpose. There is the time the light has traveled. There is the distance to the source when the light was emitted. There is the distance to that source now, after expansion has changed the scale of space. Astronomers must be careful about which one they mean, because the answers can differ enormously. This is why popular statements about the size of the observable universe can sound puzzling. The age of the universe and the width of the visible region are not the same thing. Expansion complicates the geometry. The cosmos does not behave like a static stage. It is more like a stage that grows while the actors, signals, and measurements are already in motion. The observable universe is wider than its age suggests. The universe is about 14 billion years old, but the observable region is much wider than 14 billion light-years across. This surprises many people because light speed seems to set a simple limit. If light has had only that much time to travel, how can the visible universe be larger? The answer is expansion. While light from ancient sources was traveling toward us, the space between here and there continued to grow. The light did not need to cross today's full distance all at once. It crossed a changing cosmic landscape. By the time it arrived, the region that emitted it had been carried much farther away. This means the diameter of the observable universe is far larger than a simple age multiplied by light speed would suggest. The difference is not a trick. It is one of the clearest signs that the universe is dynamic. Its size is not just measured by time. It is shaped by growth. Light began traveling long ago while space kept expanding. Picture a signal leaving a young galaxy when the universe was smaller, denser, and changing rapidly. That light begins moving toward the region that will one day contain Earth. It never stops traveling at light speed through its local space. Yet the cosmic distances around it are not fixed. Space stretches as the photon moves, lengthening the route and altering the wavelength. For much of the journey, the source may have been receding in a way that makes the geometry difficult to picture. Still, the photon eventually arrives because it began its journey under conditions that allowed the distance to be overcome. This gives ancient light a dramatic history. It has crossed a universe that changed beneath it for nearly its entire trip. When it enters a telescope, it is not only a signal from an object. It is evidence of an unfolding cosmic environment. Its path records billions of years of expansion in silence. The farthest visible regions are now much farther away. When we observe the deepest regions of the universe, we see them as they were in extreme youth. Their present-day locations, if we could define them across cosmic time, are far beyond the distances suggested by the age of the light alone. Expansion has carried them outward, while their ancient photons moved inward. This is why the observable universe can include regions that are now tens of billions of light-years away. We are not seeing them as nearby objects from the present. We are receiving old light from when they were closer, and the universe was younger. Their current state is not available to us in any direct way. In some cases, it may never be. This creates a deep separation between image and reality. The sky shows us a historical version of the distant universe, while the present version has moved beyond ordinary access. The farthest visible regions are both part of our evidence and far outside our practical reach. Cosmic distance depends on how you choose to measure it. Astronomers use different definitions of distance because the expanding universe demands them. Look-back time tells us how long light has been traveling. Comoving distance describes positions in a way that expands with the universe. Luminosity distance tells us how faint an object appears. Angular diameter distance relates true size to apparent size in the sky. These are not contradictions. They are different tools for different questions. A galaxy can have one distance according to light travel time and another according to its current separation in the cosmic expansion. This can sound confusing, but it is actually a sign of precision. The universe is complicated enough that a single everyday meaning of distance is not enough. Scientists must ask exactly what they want to know. How old is the light? How far is the source now? How bright should it appear? How large should it look? Each answer reveals a different piece of the cosmic structure. The universe may be almost perfectly uniform on huge scales. On small scales, the universe is full of contrast. Stars gather into galaxies, galaxies gather into clusters, and enormous voids open between them. But when astronomers average over truly vast distances, the cosmos appears remarkably even. No direction seems to contain a completely different kind of universe. No enormous region obviously breaks the broad pattern. This large-scale uniformity is one of the foundations of modern cosmology. It allows scientists to model the universe as a whole, rather than treating every region as unrelated. The idea does not deny local complexity. Instead, it says that if your view becomes wide enough, the clumps and gaps begin to balance out. This is astonishing because the universe could have been wildly uneven from the start. Instead, it seems to have a grand statistical order. The largest view is not chaotic in the way the nearby sky might suggest. Beneath the detail, there is a deep and measurable smoothness. Smoothness across the sky is one clue for inflation. The ancient background radiation has nearly the same temperature in every direction. That is surprising because widely separated regions of the early universe should not have had enough time to exchange energy if expansion followed a simple path from the beginning. Inflation offers a possible solution. Before being flung far apart, those regions may have been close enough to reach a shared state. Then rapid expansion stretched them across distances that now lie on opposite sides of our sky. This explains why the early universe looks so evenly balanced. It is like finding two distant rooms with the same temperature, then discovering they were once part of a much smaller connected space. The smoothness does not prove inflation by itself, but it is one of the reasons the idea became so powerful. The sky seems to remember a time when far separated regions were once intimately connected, before space grew beyond ordinary intuition. Inflation explains why distant regions share nearly matching temperatures. Temperature matching across the ancient sky is one of cosmology's great puzzles. Regions separated by enormous distances appear to have almost the same thermal history. Without inflation, it is difficult to explain how they coordinated so well. They should not have had time to send signals, exchange heat, or settle into balance before the oldest light was released. Inflation changes that starting point. It suggests the regions were once close together, within a small domain where physical interactions could even things out. Then an immense burst of expansion stretched that domain across the cosmos we observe. The result is a sky that looks coordinated because it grew from a once connected patch. This is powerful because it turns a mystery of sameness into a story of separation after unity. The universe appears uniform not because distant regions somehow communicated across impossible distances, but because they may have shared a common beginning before the stretching made them remote. Without inflation, the early universe looks mysteriously coordinated. If we remove inflation from the story, the uniformity of the early universe becomes harder to understand. Opposite sides of the observable sky show nearly the same background temperature, yet in a simple expansion model, they were never close enough to influence one another before that light was released. It is as if two strangers on distant continents somehow prepared the same meal at the same temperature without ever sharing instructions. Physics does not like coincidences on that scale. Scientists search for mechanisms that explain why things are as they are. Inflation is one such mechanism, though not the only topic under discussion. It gives the early cosmos a way to begin in a connected state before being stretched enormously. Without it, the smoothness remains a deep challenge. The puzzle is not that the universe has small differences. The puzzle is that it is so similar across such great distances. Its ancient coordination asks for an explanation. The horizon problem asks how separated regions became so similar. This problem begins with a simple question. How did regions of the early universe, now seen in opposite directions, end up with nearly the same temperature if they could not have exchanged signals? A horizon, in this context, is the distance over which information could have traveled by a certain time. If two regions lie outside each other's horizons, they should not be able to coordinate their conditions. Yet the cosmic background suggests a striking level of agreement. This mismatch is called the horizon problem. It is one reason inflation became so influential. By proposing that those distant regions were once much closer, inflation allows them to share conditions before rapid expansion separated them. The problem matters because it shows how observations can force theory to evolve. A smooth sky might seem simple, even unremarkable, but it contains a deep question. The universe looks connected in ways that its earliest visible geometry does not easily explain. The edge of knowledge often becomes the beginning of theory. Science does not stop when direct observation reaches a boundary. It changes method. At the cosmic edge, researchers cannot simply travel outward and take samples. They work with signals, patterns, equations, and predictions. A theory earns attention when it explains what is already known and suggests what else should be found. This is how cosmology moves beyond the visible limit without pretending certainty. Inflation, dark matter, dark energy, cosmic topology, and multiverse ideas all occupy different places on the spectrum between evidence and speculation. Some are strongly supported by many observations. Others remain possible but unconfirmed. The edge of knowledge is therefore not a blank wall. It is a workshop. Scientists build models there, test them against every available clue, and discard the ones that fail. The boundary between known and unknown becomes active. It is where imagination must become disciplined and where wonder is sharpened by the demand for evidence. Dark matter shapes the visible universe without revealing its nature. Galaxies rotate in ways that cannot be explained by their visible stars and gas alone. Galaxy clusters bend light more strongly than ordinary matter can account for. The large-scale structure of the universe also points toward a hidden form of mass. Scientists call it dark matter because it does not shine, absorb, or reflect light in any ordinary way. Its gravity, however, is written across the cosmos. It helped pull ordinary matter into the web of galaxies we observe today. Without it, structure may not have grown quickly enough after the early universe. Yet its identity remains unknown. It may be made of particles not yet detected, or it may point toward deeper physics. What makes dark matter so compelling is its combination of influence and invisibility. It is not a minor missing ingredient. It is a major architect of the observable universe, shaping what we see while refusing to show itself directly. Dark energy controls the future edge of cosmic discovery. Dark energy does not build galaxies or bind stars together. Its influence appears on the grandest scales, where it drives the accelerated expansion of the universe. Because of that acceleration, the future boundary of what can ever be observed is changing. More distant regions will slip beyond communication, and their new light will never reach us. In this sense, dark energy is not only a mystery about cosmic expansion, it is a force that decides the long-term reach of knowledge. If it remains steady, the universe will become more isolated over time. If it changes, the future could unfold differently. Scientists measure its effects through supernova, galaxy clustering, and the background radiation, but its physical nature is still unknown. It may be a property of empty space, or a sign that our understanding of gravity is incomplete. Whatever the answer, it shapes the ultimate horizon. It governs how much of the cosmos remains discoverable. The universe's fate depends on forces we barely understand. The long-term future of the cosmos is controlled by ingredients that remain deeply mysterious. Dark matter-shaped structure, but its particle nature is unknown. Dark energy accelerates expansion, but its origin is unclear. Gravity works beautifully in many tests, yet it does not fit easily with quantum physics. These unresolved pieces matter because they determine the universe's destiny. Will expansion continue forever? Will it accelerate without end? Could dark energy change over time? Could a deeper theory revise the entire picture? Cosmology is not only the study of what happened long ago, it is also the attempt to forecast the fate of everything. The remarkable part is how much we already know, and how much depends on things we do not yet understand. The universe has given us enough evidence to build a powerful model, but the final chapters still rest on hidden mechanisms. The future is written in physics that remains partly unread. Endless expansion may leave galaxies isolated in darkness. If accelerated expansion continues, distant galaxies will drift beyond view, and gravitationally bound groups will become increasingly alone. The Milky Way and Andromeda are expected to merge long before the far future emptiness fully arrives. Their descendant system may remain surrounded by its own stars, remnants, and dark matter halo. But beyond that local island, the wider universe could fade from detection. New starlight from remote galaxies would never arrive. The cosmic background would become stretched toward wavelengths so long that it would be nearly impossible to recognize. To future observers, the universe might appear as a single vast galaxy surrounded by darkness. They may not easily discover that a larger cosmic web ever existed. This possibility gives the present night sky a special significance. We can still see beyond our local gravitational home. We can still measure distant galaxies and trace cosmic history. In a universe of endless expansion, that broad view may be temporary. A distant future may contain only cold, fading remnants. Stars cannot shine forever. They burn fuel, evolve, and leave behind white dwarfs, neutron stars, or black holes. New stars can form from gas, but over immense timescales, usable gas becomes locked away or dispersed. If the universe continues expanding, star formation will gradually decline. The bright era of galaxies will fade into an age dominated by remnants. White dwarfs will cool. Neutron stars will spin down. Black holes will persist for extraordinary lengths of time. Planets, if they survive, may orbit dead suns in darkness. This is often called the heat-death picture, though the full future depends on physics still under study. It is not dramatic like an explosion. It is a slow thinning of usable energy. The universe becomes less able to create new structure, new light, or new complexity. That future is difficult to imagine because it unfolds across times far beyond human history. Yet it may be where cosmic time is pointing. Some theories imagine a final horizon around every surviving galaxy. In an accelerating universe, each gravitationally bound region may eventually become surrounded by its own cosmic horizon. Anything beyond that boundary would be unable to send new information inward. For an observer in a far future galaxy, the reachable universe could shrink in practical terms to the local system and its remnants. This resembles the way a black hole has a horizon, though the physics is not identical. The horizon would not be a surface you could touch. It would be a limit on communication caused by expansion. Beyond it, events could continue, but their signals would never arrive. This gives the future universe a strangely private character. Each remaining island of matter may have its own limited sky, cut off from the larger whole. The cosmos would not need walls to become divided. Expansion alone could draw the lines. The final frontier may be less like an outer edge and more like countless isolated horizons. Black holes may become the last bright engines of time. Long after ordinary stars fade, black holes may remain as some of the most important objects in the universe. They can store enormous mass in compact regions, shape the motion of surrounding remnants, and release energy when matter falls into them. In the distant future, active feeding may become rare because loose gas and stars will be depleted or scattered. But black holes themselves can endure for almost unimaginable spans. Supermassive black holes in galactic centers could outlast the bright stellar age by vast margins. They are not eternal according to current theory, but their lifetimes can be so long that human numbers feel useless. In a darkening cosmos, they may be among the final great structures left. Around them, gravity remains intense, time behaves strangely, and the memory of former galaxies is concentrated into darkness. The universe may end not with a blaze of stars, but with black holes waiting through ages almost beyond meaning. Hawking radiation could outlast the stars by unimaginable ages. Quantum theory suggests that black holes are not perfectly permanent. They may emit an extremely faint form of radiation because of effects near the event horizon. For ordinary stellar mass black holes, this radiation is so weak that it is overwhelmed by the cosmic environment today. But in the far future, after stars have faded and space has cooled, it could become significant. A black hole would slowly lose mass, shrinking over stretches of time so vast that they dwarf the age of the universe. Smaller black holes would evaporate faster than larger ones, while supermassive black holes could survive for almost inconceivable durations. This idea, proposed by Stephen Hawking, connects gravity, quantum physics, and thermodynamics in a profound way. It suggests that even the darkest objects have a final whisper. If the theory is correct, the last major events in the universe may be faint releases of energy from black holes finally disappearing. Even the far future has horizons we cannot fully picture. The end of the universe is not a single, settled story. Scientists can project likely futures based on current measurements, but those projections depend on unknowns. Dark energy may remain constant, or it may change. New physics could alter our understanding of black holes, vacuum energy, or the ultimate stability of matter. Even if the broad path is endless expansion, the details reach into timescales that break ordinary imagination. Human thought is comfortable with years, centuries, and perhaps millions of years. Cosmology asks us to consider duration so extreme that stars, galaxies, and black holes become temporary phases. At those scales, even familiar laws may need deeper interpretation. This is why the far future has its own horizon. Not only a boundary of light or motion, but a boundary of comprehension. We can sketch possibilities, but we cannot pretend to see every detail. The universe ahead is as humbling as the universe behind us. The universe may end in thinning darkness rather than a wall. Many people imagine the end of the universe as a final boundary, a collapse, or a dramatic last moment. Current evidence points more toward a quieter possibility. If expansion continues and usable energy spreads ever thinner, the cosmos may gradually lose its ability to make new bright structures. Galaxies outside local groups fade from view. Stars burn out. Remnants cool. Black holes slowly evaporate across staggering timescales. There is no wall at the edge, and perhaps no final crash. Instead, there may be a long decline in contrast, activity, and accessible energy. This is not an ending in the ordinary storytelling sense. It is an approach toward emptiness and equilibrium. The universe does not need to close like a door. It may simply become less able to change. That possibility is haunting because it is so patient. The final state may not announce itself. It may arrive through a silence that deepens without limit. The edge may be a horizon, a history, and a mystery. The word edge sounds simple, but cosmology turns it into several ideas at once. There is the horizon of what we can see, shaped by ancient light. There is the horizon of what can never reach us, shaped by accelerated expansion. There is the historical edge, where the universe becomes opaque to direct vision. There is also the conceptual edge, where ordinary language struggles with space, time, and existence itself. None of these is a physical rim you could approach and touch. Each is a boundary of knowledge, contact, or interpretation. That is why the subject is so compelling. It begins with a childlike question, where does everything end, and leads into the deepest structures of physics. The edge is not one place. It is a set of limits that reveal how the universe works. Every horizon tells us something, not only about what lies beyond it, but about the nature of seeing. Every new telescope pushes the edge of sight a little farther. The history of astronomy is a history of enlarged vision. The first telescopes revealed moons around Jupiter and stars invisible to the naked eye. Later instruments resolved nebulae into galaxies and measured the expansion of the universe. Space telescopes lifted our view above the blurring atmosphere. Infrared observatories now reach toward the earliest galaxies whose light has been stretched by cosmic time. Each new instrument does not merely add prettier images. It changes the questions scientists can ask. Fainter objects become measurable. More distant eras become accessible. Old theories face sharper tests. The edge of sight moves outward, not because the universe changes for us, but because our ability to receive its signals improves. Even so, there will always be limits. A better telescope can gather more light, but it cannot overturn the speed of light or erase cosmic horizons. The frontier advances, and still the deeper mystery remains ahead. We are trapped inside the universe, yet able to measure it. There is no outside platform from which to view the cosmos as a whole. We cannot step beyond space, turn around, and inspect its shape from a distance. Every measurement we make happens from within the system being studied. That would seem like a severe disadvantage, and in some ways it is. Yet it is also one of the triumphs of science that we can learn so much from inside. By measuring light, motion, temperature, gravity, and the distribution of matter, humans have reconstructed a history spanning billions of years. We have inferred invisible components, tested geometry, and estimated the age and expansion of the observable universe. This is astonishing. A small species on one planet has found ways to measure the arena that contains every planet, every star, and every galaxy it can see. We are enclosed by the universe, but not blind within it. Our instruments turn local observation into cosmic understanding. The greatest unknown may begin just beyond our oldest light. The oldest direct signal gives us an extraordinary boundary, but it also marks the beginning of deeper uncertainty. Beyond that light lies the earlier universe, when conditions were hotter, denser, and harder to probe directly. There may be clues from gravitational waves, particle physics, and subtle patterns left in later radiation, but the direct image stops. This hidden chapter may contain answers to some of the largest questions. What happened at the earliest moments? Did inflation occur? What set the initial conditions? Are there signs of physics beyond current theories? The region beyond our oldest light is not a place farther away in the usual sense. It is an earlier state of everything. To study it, scientists must combine observation with theory at the edge of what can be tested. That is where the unknown becomes especially powerful. The universe has shown us its childhood photograph, but not yet the secret of its birth. The edge of the universe may be where certainty turns into wonder. At the largest scales, knowledge and mystery are not enemies. They depend on each other. We know enough to understand that the visible universe has horizons, that light carries history, and that expansion shapes what can ever be reached. We know enough to reject simple pictures of a wall at the end of space. Yet the same knowledge opens deeper questions. What lies beyond the observable region? Is space infinite? Did inflation create other cosmic domains? Will the evidence available today vanish from future skies? The edge is therefore not a failure of understanding. It is the place where understanding becomes honest about its limits. That honesty is what makes the subject so moving. The universe gives us measurements precise enough to build confidence, then vastness large enough to keep humility alive. At the edge, science does not become less powerful. It becomes more human. It tells us what can be known, and lets wonder begin where certainty ends. And so, we come back from the edge of the universe. Tonight, we followed the limits of sight, where the oldest light still reaches us after crossing almost all of cosmic history. We explored horizons that are not walls, but boundaries of time, distance, and possibility. We imagined galaxies beyond contact, regions beyond measurement, and a universe that may continue farther than any telescope can ever prove. We drifted through the strange stretching of light, the hidden shape of space, and the deep mystery of what may lie beyond our observable world. Some ideas were grounded in evidence. Others waited at the frontier, where careful science meets the unknown. And through it all, the same quiet truth remained. The edge of the universe is not simply a place. It is a question. Now, let that question soften. There is nothing more you need to follow. Nothing more you need to solve. Let the vastness fade into the background, like distant starlight becoming small and calm in the mind. Feel your shoulders loosen. Let your breathing settle into its own easy rhythm. Allow your thoughts to grow slower, as if they are floating outward through a wide and peaceful dark. If you enjoyed this curious journey, you're welcome to like, subscribe, or leave a thought below. It helps others find their way here too, one sleepy soul at a time. And if you are still awake, there will be another gentle exploration waiting on the screen, ready whenever you are. But for now, let the universe be wide, without needing to understand it all. Let the night hold the questions. Let your mind rest at the edge of wonder. Sleep well, and good night.